Anyway. Okay. So what we were talking about last time, I got a little bit stuck towards the end when we talked about transforming the kinetic energy operator to cylindrical coordinates as tractable, all of the homework. That a person can sit down and do on pen and paper without too much trouble. Forget 3D, we're not doing that. Although I'll write that down later. Let's see, okay, so once you go through that rigmarole, and what I'm doing here is separability, so I've acted on the right with a trial wave function where there is a radial and an angular component. We only have one angle, which is rho. And what I'm doing here is trying to evaluate, what am I doing? I can do it this way. I like doing things, what have I done? I'm already messing up. Sorry, I'm going to do this. Oh, God, I'm looking at two different things at once and I just got confused. Sorry about that. Okay, so this is near the end of what we were at last time, and I'll show you a little bit. I remember I was saying I got a little confused about something, and I'll explain it and then show you why I got confused, because that might actually be useful. Remember that we also now have two m's. We have a angular quantum number, usually called m sub l, so that you don't confuse it with m, which is mass. Stuff happens. Anyway, okay, now, so kinetic energy operator, I've done some algebra. I've multiplied by r squared, and blah, blah, blah. So the point here is that you've got the acting on the right with a wave function composed of two functions, one of r and one of phi. And then you divide on the left by the same. What you're checking for are separate terms, added or subtracted. Remember, subtraction is just the addition of something negative. R, phi, r. Okay, so that's separated. And that means that the trial solution of a function of r times a function of phi is actually correct. Okay, where I got flubbed a little bit is right here. And what I remembered was, when I was reviewing my notes, is when you're in this situation, every one of these, the different r's and ph's, they have to add up to constants. Now, where I got a little confused was I wanted to separate energy into portions and give one portion to r and give another portion to phi. Now the reason, and so I was thinking that because that's what you do with a particle in a box. When you're doing a multi-dimensional particle in a box, you just take whatever the total energy is, you get half of it to the x dimension and the other half to the y dimension. And that's actually the equal partition theorem. Every degree of freedom, and that just means motion in x or y, picks up an equal portion of energy. And that's the equal partition theorem. The reason you cannot do that here is because the energy belongs to the radial, right? So here's the energy. It's part of the R, little miniature Schrödinger equation. And so I'm only going to solve the energy when I'm looking at the radial part. So that means that all of these terms are adding up to a constant. So what you do here is let's just make this guy a constant. Let's just call it minus, I think it's minus m sub l squared. We're just going to call it that. Now, the reason is that when you solve this damn thing, you end up with a very familiar looking equation, minus m sub l squared. And I also want to point out, I noticed that, so all of this is a constant. Now, the rest of this stuff is going to be equal to minus that constant. I'll explain that in a minute, but anyway. You may notice that I'm giving this a very specific result. Why can I presume that? Why can I presume that all of this is going to be minus a number squared? Because I haven't said what it is. Well, who says it's negative? Who says it's negative? This can be complex, and the result can be positive. right? So I haven't really pigeonholed myself into saying what this is. I've just given it a convenient form because this makes the solution easy. Now, hopefully we've all seen enough of this to know that the solution is, of course, e to the IM And now you can see that the double derivative brings down an I squared, m squared, n sub l squared, and that's why I'm saying the whole shebang is equal to minus m sub l. Anyway, so like I say, what I got confused about last time is that I wasn't sure what constant it was equal to. I was thinking like, oh wait, is that energy in the angle part and the rest of this is energy in the radial part? And the answer is no. All the energy belongs to the radial, and this ends up being kind of funkified. And I don't know that I can really explain it that well. I'm going to say it kind of mathematically turns out that way. Okay, the next part is to note that the way the other part works is because all of this has to be equal to a constant. If you bring that energy, what I'm doing is I'm now unpacking the differential equation in the radial part. And by that I mean I've taken that division by the wave function on the left and I've multiplied it out. Okay, so, and now I'm bringing over the r squared 2me over h bar squared, and here's again the solution, and here's the deal. All of this is now equal to plus m sub l squared. All right, but of course, it's a wave equation, right? So it still has kind of a wave function there. And that's just how eigenvalue equations work, and we're always dealing with eigenvalue equations. So again, if this damn part, if I bring this guy over, I hate to do this to you, but if I bring this guy over and set the whole thing equal to 0, which is totally legit, obviously, if this is minus m sub l squared, then the rest of it is equal to plus m sub l squared, which is what I've done here, right? So that way, it's all equal to 0. So that's how it's done. Anyway, so I hope I explained it a little bit better than I did last time. And then I wanted to point out that Bessel solved, back in the day, they just simply wrote down equations and said, oh, let's solve this one. And I'm not joking, I literally think they did it that way. But although I did mention that there is apparently some relationship to some engineering problems that they knew about even back way back then. Sidebar. So again, so I'm just writing down. Sorry. I'm writing down Bessel's equation. I'm just not following my notes. Sorry. That's what I just wrote down. Okay, here's how Bessel did this. So this is what he felt was necessary to solve for whatever the hell reason he had to solve it. So there you go. And this is called the order. Order of the, you have to plug a number in there and solve it. Then let's say alpha is 0. So when Bessel solved this, he has to plug in a value there and solve it. And then when he plugs in a different value, he has to solve it a completely different way. Now you may know alpha of 0 as basically an S state. Because notice that in our language that's our m sub l. So that's the rotational component. Alpha of 1 is basically going to be a T state. Not quite, because it's two-dimensional, but still though. I think you can imagine a drum where it's vibrating like right in the center. That's an S state. Now imagine a drum where it's been hit, right? So it's vibrating left and right? And that would be like a P-like state. And I can show some examples off MATLAB, maybe next time. Okay, so there you go. Now the solution is, actually, do you folks remember solving, how did you do this? There's a method called the method of successive approximations for solving some kind of calculus problem, like solving for derivatives. So when you plug in a number into the equation, and you do the operations, and you plug that result back in, and you do that over and over again. Anyway, look, there's little approximate ways to do calculus problems. You should have seen that in Calc 1. Anyway, it's conceptually a very simple way to solve derivatives, something like that. Not differential equations. Again, it was just something very simple. There is a way to solve differential equations which is similar, and I forgot the name of it, but whatever. This is how it was applied, and when you use this method to solve differential equations, you end up with series, like a Taylor series or something that looks just like a Taylor series. And I wrote this out last time, just bears repeating. And these are Bessel functions. So just Bessel functions. Now you may have heard the term spherical Bessel functions, which is fine. That is the 3D case. R over 2 to the 2m. I think I kind of got myself. I hope you can see it okay. And a gamma function. You run into gamma functions a lot in physical science. So it's whatever the argument is. The argument shows up in kind of a weird spot. This is x to the z minus 1, e to the minus x. Anyway, so gamma functions are very common in science, this and that, so you'll see this quite a bit. Okay, so now I also want to emphasize that Bessel functions are like sine functions. I mean, if you think about it, I know you're incredibly familiar, you know, a sine function doesn't like it bother you, right? But this Bessel function, you're like, oh, what the hell is that? It's something that, like, if I'm working with Bessel functions, I just use MATLAB. Hey, MATLAB, for the 0 with the Bessel function, what's the Bessel function for 0, for point 1, for point 2, for point 3, for point right? So I'm just plotting it. I mean, I can plot a sine function the same way, so there's nothing really mysterious about it. It's just, instead of like a e to the x function, it's more like a sine function, where there's actually a little bit of obscurity in terms of what comes in and what comes out. But by familiarity, you know, you're just not uncomfortable with them. Anyway, just wanted to point that out. Okay, let's look at the S-like state. Now, this is a mistake, by the way. I just want to point out. I'm going to add R. I'm going to say that I'm going to plug in R. Now, that can't be correct, and I'll explain that in a minute. Okay, this is an S-like. Remember that this is the order of the Bessel function, which is basically the angular quantum number, and I'm calling it 0. So therefore, J1 R is P-like. Okay. Now let's look at what these. Let's plot them, and they look like this. Let's do the J of 0. Okay. Now here's something that's kind of interesting. So here's our S state. Okay. Now remember that at one point, you've probably forgotten about this, we're trying to do the particle in a sphere. Just like in a particle in a box, we have to pick the solution to stop at the boundary. It's got to be 0 at the boundary, right? Because if it steps out the boundary, it's now in an infinite potential surface. It requires infinite amount of energy to do so, and there's not infinite amount of energy in the universe. Okay, so the funky thing here, is that Bessel functions keep on going. They go and go and go like the Energizer rabbit, and they're very specific, by the way. If I use MATLAB, the first 0 is at about 2.4. Now, I'm not 2.4 nanometers, 2.4 meters, 2.4 cats. What am I talking about? I'm not talking about anything. 2.4, no units. Now that should be a clue that I've actually done something wrong here. R has units. But if I use MATLAB, I cannot plug in units. So this is not correct. I'll explain what the actual thing here is in a minute. Anyway, so that's the J of 0, the S function. Okay, so now let's do I have to get this out of the way. Let's do the p state. Now the p state, if you remember your hydrogen atom, this and that, just like a hydrogen atom, it starts at the origin, so it's a little different in that regard. Okay. Always define your axes. When you have your exams, we start yelling at you if you don't have your axes labeled on the graph. Because we're terrified that you don't know what they are, actually. So, anyway, all right, so this is the p-like state. There you go. And, okay, as much as this one was at 2.4, it has a 0 at 3.83, right there. And there's other zeros out here. Okay, so this is kind of funky, right? I want the function to end at the boundary. I want it to just go down, you know, just to plop down to 0 and stop. But it doesn't. So how do I interpret that? You know, a sine function does the same thing, really. I mean, I just made the ground state. I made the argument of the sine function basically pi x over L because at the boundary it hits 0. But it technically goes on. I just kind of pretend that it doesn't, right? A sine function does. Okay, I'm actually seeing the same behavior here. So now it opens itself up to interpretation. Okay, so the way this works is, all right, I'm talking about, let's look at the S state and I'll explain the P state in a second. Let's look at the S state. Let me show you what a 1s state is. It's this. Now, let me show you what a 2s state is. It's this one. This is the 2s. It bothers me that it's not centered into the graph. It needs to be centered because that's perfect. Okay, so here's the deal. Just like hydrogen has a 1s, a 2s, a 3s, a 4s, a 5s, after you get to 6, right? I think we're at the transuranium elements and atoms aren't stable anymore. But there you go. So the way you interpret the fact that these waves keep on going is that if this is your boundary, let's call it boundary A, like before. Oh, I just made this big deal about labeling your axes. There you go, R and J. If the Bessel function contorts such that it has no nodes and stops at A, that makes it a 1s. If it stops at A but has a node, that makes it a 2s. If it had 3 nodes, it would be a 3s function. Okay, now we can play the game for the P state. J1. So a 1P state looks like this. Again, it goes a little bit further than the 1s, so this is a 1P state. And then we have a 2P state, which again, at this point, I think you know how this game works. It's going to do this. So there you go. Okay, so that's 1P, this is a 2P state. It also points out the fact that there is a 2P, there is a 1P state. I know that there should be a 2P state because I'm kind of wanting this to look like hydrogen, but it's not hydrogen. And I know that because it actually has a 1P state. There's even a 1D and a 1F state. So that's where the particle in the ring, particle in a circle, particle in a sphere does the same thing. That's where it's a little different than the hydrogen, that you can get things like 1P and 1D states, whereas hydrogen doesn't. Okay. Now, last bit is, as I mentioned, you can't have the argument actually be R. That actually doesn't make sense because you can't, just like you can't plug in sign of energy. That, again, is just absolute nonsense. It's scientific nonsense, and the reason is that in a series, the argument ends up being like, argument plus argument squared plus argument cubed. And a science equation, any science equation, math, engineering, whatever, that has meters plus meters squared plus meters cubed, that's nonsense. You can never do that. I mean, you can do it, you're just an idiot and you're describing Babel. So, heads up on that. All right, so the way it really works is not like this. It works like this. All right, I'll talk about an S state. You make it KR, where K is our usual 2ME over h bar squared, which guess what, is proportional to 1 over a meter. I'm assuming we're working in that size, so kilograms, joules, and joule seconds on h bar. Get this. Do the unit analysis, and our k's, which are wave vectors, which are momenta, right? It's almost momentum. You just need to divide it by h bar. I keep forgetting. Then multiply it by h bar, and then it's momentum. The damnedest thing is they have units of 1 over meters. Okay, so now kr 1 over meters times meters. Now there's no units to the argument, which is required. Okay, now the neat thing about that is, now I can look at these graphs and calculate the energy. And that ends up being really easy. Okay, now remember that the boundary condition on the, let's do the 1s state. So it's a J0. Now, let's say at A, when R is A, okay, I'll make that clear by doing it like this. R is equal to A. Just so you know I'm not like suddenly changing, you know, I'm like not talking about space, but anyway. So K times A, when K times A is fed into J naught, J0, 1s, you better get a 0. Okay, so that's how that works. Now, as usual, boundary conditions are the things that answer questions, especially at this, you know, especially these flat potential deals. What does it answer? Well, let's look at this. Okay, so K is 2ME, I just did it, 2ME over h bar squared times the radius of the particle in the sphere is 2.4. Right? See how that works? Remember that the Bessel, the 1s state, when it's fed the number 2.4, the J0, 2.4 equals 0. What is it being fed? K times the radius, and that satisfies the boundary condition. So K times the radius equals 2.4. Therefore, let's see here. Okay, 2.4 times h bar. I'm kind of cheating here. Okay, so then I square it, a squared, and then divide by 2m. E of the 1s state. Did I do that right? I feel like I've made some kind of weird mistake. No, I did this right. Yeah, I did that right. Okay, so there you go. So now I've got the energy of the 2s state. So it's kind of funky. You have to plug in the 0 and multiply it by a bunch of constants, and that gives you the energy of the particle in the sphere at the ground state. So now if you're interested in the energy of the 2s state, instead of 2.4, you plug in, actually it's here, it's 5.52. These are tabulated, by the way. These numbers are like way important for tons of stuff. If you want the energy of the 2p state, sorry, the 1p state, you plug in 3.83 right there, and there's your energy of the p state, 1p state. So anyway, that's how it goes. Not too hard, just a bunch of detail. The last bit I wanted to cover. Now, I know my former students have seen this, but it bears repeating. I actually forgot this when I had to teach quantum for the first time.
I have a question. So this equation that we got, the Bessel's equation. So that Bessel's equation, we are getting from that equation?
Bessel back in 17 something felt like solving this, because why wouldn't you, back in 1700, and was able to figure this out. Right. And that's what now plug this in the MATLAB, because I mean, damn, look at it, right? Now, in honesty, I'm not nearly, I mean, this looks kind of scary, but in all honesty, if you get really good with your MATLAB, this is, I'm looking at it like, yeah, that's not too hard. Also, gamma functions are something that are built into MATLAB, so that part doesn't bother me. Actually, Bessel functions are built into MATLAB. And so you plot them, and that's what they look like. Again, you have to tell MATLAB, it says, oh, you want to plot a Bessel function? Which one? Oh, I want the 0 Bessel function. I want the 1 Bessel function. And it plots exactly that out. Right, and that's how, then that's it, basically. All right? Okay? So next bit, when I was looking at this again for the first time in a while, I actually got confused about where px, py, and pz orbitals came from. And it turns out, okay, so on the surface of things, let's do, now we have to do a 1p. Let's do the 1p state. Kr. So that's J1, Kr. Okay, now remember that there will actually be 2 of them. So I know that you're used to there being 3 p states, px, py, and pz, but we don't have this here. There's no z, right? So there's only 2 of them. So you have two solutions. Right, so m sub l is 1, actually, or minus 1. So you end up with 2 solutions. Now, it turns out that these are traveling waves. If we look at the angle part. Now, a traveling wave is going to look like this. If we propagate it over time, it's doing this. So that's all fine and good. So there you go. You can kind of visualize that. I didn't draw it super well, but it's moving along. Now that's a traveling wave versus a standing wave. All right, you can imagine I'm just like, if I had a string and I'm like waving on it, I'm going to get this. But if I get it just right, I might actually see this. So here's a wave, but instead of the amplitude traveling, what can happen is the amplitude just weakens, and then it goes the other way. And then it weakens, and then it goes the other way. Then it goes back. So the crest of the wave is always right here. So here, you can see the crest of the wave, if you can imagine it propagating in time, you can see the crest of the wave kind of like traveling. That's why we call it a traveling wave. Whereas in a stationary wave, the crest of the wave is just, it's, instead of doing this, traveling, instead of doing this like my cat. So, I think you can all visualize that. Now, these are traveling waves, and we consider those unsatisfactory for quantum. Now, the fact is, I want to emphasize something. This is kind of funky. What I'm going to do is absolutely arbitrary. I don't have to do this. There's no reason to do this other than it feels good. These are solutions. They're fine. But you can make linear combinations. You can make linear combinations of them as well. Notice that the Bessel functions are the same. So you can do this. Remember, any combination is fine. Right? And that's basically cosine and basically sine. So this would be px, and this is py. Because, right, y, x in cylindrical coordinates is r cosine, and y in cylindrical coordinates is r sine. Now, again, I want to emphasize, what you know as px and py and pz orbitals, they're created this way as linear combinations of traveling waves because we just feel that the answer should actually be stationary. There's another thing. For undergrads, for freshmen, are you going to show them a complex wave function? Or are you going to show them a sine and cosine? Because they get sine and cosine. Here's another problem. visualizing these means you have to draw a graph, you have to show it twice. You have to show the real and imaginary. Are you going to show that to a freshman? Say, oh, here's the imaginary component. What? Or you make linear combinations, which is perfectly valid. You get stationary waves, and it's fully real. So this is how we do it. But I want to emphasize that you don't have to. In fact, it's an extra unnecessary step simply to make nice-looking graphs for our undergrads. Now, the reason I bring that up is often I'll see solutions that don't do this. Like if you're using Gaussian for electronic structure theory, they don't bother to do this. Why would they? Right? So look out for that. So I also want to emphasize that what you think of as that's the solution is actually not no. Anyway, I thought that was kind of fun. Okay, anyway, so that's particle in a circle. So now I want to cover particle in a sphere. The solutions, the Bessel functions for particle in a sphere, they're not the same. So the problem is basically the same. It's just that now you've got to work in spherical coordinates. You've got to write out the 3D spherical kinetic energy operator, and I'll write that down in a minute. And Bessel solved that thing too, because why not? And the functions are not quite the same. The end results are similar, but not exactly the same. So one thing that confused me for the longest time is I always heard Bessel functions, and then I heard spherical Bessel functions, and I just thought that was the same, different words for the same thing, and it's not. Bessel functions are for 2 dimensions, spherical Bessel functions are for 3 dimensions. Anyway, I'm getting ahead of myself. Okay, so note in 3D, and I hope you appreciate the fact I didn't make you do numbers 4, 5, 6, 7, and 8 for 3 dimensions, right? So instead of r cos, I've got r cosine, right? You didn't have the sine theta before. Question?
So, last one, the cylinder was 2D, right?
Yeah, that's all 2D, right? I only have one angle. That's how you know.
R and phi. Then now we have 3D.
Now let's do 3D. Why not? Yeah. Now again, I always do the 2D. I spend a long time on 2D because that's one that you can solve the kinetic energy operator with without hideous difficulty. I mean, as much difficulty as what's on the homework, right? And I obviously you saw I tried to walk you through because I didn't want you like going crazy.
If we solve the 3D and say that the phi is 0, then can we go to the 2D?
Yeah, when you write out the kinetic, that's actually a homework problem that I think they had to do. If you write out the 3D kinetic energy operator and you say theta is 0, it turns into the 2D. It's exactly the same. Yeah. It's a way to double check yourself. Okay. Okay, now again, having done the homework, you see how to do this, right? Change x into, a function of r, a function of theta, a function of phi, or you didn't have theta before. And imagine this, you're going to get a more complicated kinetic energy expression. And it's pretty awful. I mean, no doubt. I'm actually surprised it's not worse than it is. I think I have it memorized actually, but I don't want to mess this up. Oh, yeah. And one of the problems that we face is that I've got R's and theta. I've got R and a theta together. That's bad. Remember that I need to. Oh, what the hell? I got R and a theta and a phi all together in one term. That's not separated. So that's as bad as we can get. Now, here's a wave function. I haven't assumed that it's separable, but of course it is. We're going to assume a radial potential. Remember I spoke at length about how potential energies are always spatial. They're always functions of x, y, and z. Okay. So anyway, all right, kinetic energy operator in 3 dimensions in spherical 3-dimensional coordinates. Now again, I hope you you can imagine how you go about figuring this out, same way as your homework, just with more. And more to the point, like I say, I started working on this once and I gave up after 2 pages because I saw I had just started. And I mean, I get that it's doable, right? Okay, now the trick is, as usual, there's a slick answer because someone already knew the solution. And when they knew the solution, they were able to tinker with a approach that worked quickly. Maybe faster than however they figured it out to begin with. Okay. Now, surprise, surprise, everything will be separable. And in fact, I've read that there's a deeper meaning to that. That unless these differential equations, if they're not separable, then they're simultaneously unsolvable in terms of an analytic form. By analytic, I mean e to the theta sine phi, versus numeric, which is a table of numbers on a supercomputer, which is how a lot of things are done. Regardless. So if I'm going to be able to write this down as a function of, sine r e to the phi, then I've got to have it separated. Now, obviously, hopefully all of you are sophisticated enough to recognize that these are the spherical harmonics. Okay. So these are the spherical harmonics, and they're traditionally written as one function, but they're really two. This is going to be e to the phi times sine beta, cosine beta. So this is separable too, but it's traditionally written as one. As written, this is not separated. It really is separated. What they're just trying to do is emphasize that you're separating the radial from the angular. Now, this is really funkified. Why am I saying that there's a function divided by r? Because again, the person who figured out the fastest way to solve it figured out that if you represent the solution this way, so you're going to solve for r, big R, if you take this approach, you get to the answer quickly. That's why it's done. When you're going to change the sucker around, you're going to be able to solve for r, and then when you want the real answer, you take the thing that comes out of your math textbook from 1800, take it from there, just make sure you divide out by r. Because that's the real answer. That gets kind of confusing. But anyway, now I'm going to plug this in, and I'm going to do some rearranging. So what happens is, oh my God, let's just do the radial part. And I'm going to ignore this. So I'm looking at this. And I'm applying this thing. So what does that look like? 1 over r squared, and the constants will be multiplied away. I'm not worried about constants right now. What I want to show you is that you can do this little operation here. So I'm doing all these operations on this function, and then okay, that's the same thing. And multiple steps later, remember I was saying that one thing to be wary of is that there are ways that these can be manipulated via product rules. They can be made bigger or smaller. Here I've taken this thing and I've made it smaller, just for the hell of it. Look out for that, because again, when I'm reading quantum mechanics, I will see the kinetic energy Hamiltonian in 3D. I will see it expressed multiple ways. When I see something I'm not comfortable with, I just know that what's happened is someone has made some kind of simplification in order to get to their solution faster. That's why they've done it. Okay, so there's this. Now let's also take the above and multiply by minus 2m, that's mass, over h bar squared, r to the 3, and then the wave function. And of course, why I'm doing this is to show separability. Okay, so again, I've simplified this, multiplied by a whole bunch of messy constants, and the end result is hopefully going to be a separable equation. Okay, so what you end up with is r squared. And remember, we'll unpack this later. By unpack, I mean you multiply everything by the wave function that you previously divided by to make sure that could do a separation, that the separated wave function was a valid one. Here's our R squared equal to, okay, I have a minus sign because it's been brought over to the right side. Okay, and then here's all the operators, there's sign. And I'm not going to spend a lot of time on this, and by that I mean I'm not going to spend any time on this. The solution to the angular part, this can be separated as well. This can be separated as well, but I'm not going to do it. The way you solve the angular wave function, all the angle bits here, is you're going to set it equal to a constant. I'm going to look in a 17th century math textbook. I may not be consistent with how I write these out. Theta, phi, theta. Okay. All right, so anyway, okay, 5 minutes left, right? Okay. So, why did I do this? And by do this, I mean why did I divide that by r? For simple mathematical convenience. So, what you can do is very quickly, you find that you've separated the r's from the angles. And that's fantastic, right? So, we need that because we're not sure we can solve anything. So I've got an R part and I've got an angle parts here, and that means each one is going to be equal to a constant, some kind of constant, and the energy will be solved within the radial part. It's like its own sub-Schrodinger equation. It's like you've got the whole Schrodinger equation, but they like funnel down into miniature Schrodinger equations, and this guy is, you're going to set this equal to a constant. And the first thing you do is you assume that the solution for phi, you assume that the phi part is still e to the I phi, im phi. That's one of the things you do. And if you make that assumption, then you can figure out the theta functions. And the two together are the spherical harmonics. So anyway, and I don't want to spend any more time on that. The constant that you arbitrarily set this equal to happens to be something that may sound familiar, L times L plus 1, where L is a quantum number that describes the solutions. And so all of this has got to be equal to like minus L times L plus 1. So again, I'm hoping that sounds familiar. You recall L times L plus 1 is like the angular energy part, right? So let's see here. I just want to point out that, again, assuming that all of this is a constant, and again, 1783 is solved, because 3D integrals comes up a lot, putting things in spherical coordinates comes up a lot, and if there's no potential, there's lots of engineering problems, so that's why in 1783 they figured this out. The fully angular parts. So again, we assume that there is a theta, there's a phi wave function, which is still e to the im phi. And so there's still an n sub L quantum number that's minus 1, minus 0, plus 1, on and on and on. The part where it gets funkified is now we have a theta. And again, it was solved in 1783, what that theta looks like. Another thing that I'm okay with this, and you hopefully will get used to it quickly, is that you see expressions like this, and this looks hideous, and it's like, what the hell is all this? By the way, this is called the Legendre, this piece of L. This is called the Legendre polynomial. Legendre polynomial. And actually, I have to double check my notes. I think the Legendre polynomial has the argument of cosine, or it's more, I have to check my notes. The argument is cosine into the the genre polynomial. So again, 1783, they solved this, but it ends up being kind of stupid. Let's look at the S state. So that's L of 0, and so M, there's only one S state, so that's why we say 0, 0. It's just 1 over square root of 4 pi. Right, it's right there. It's just a constant. Okay, if we do a P state, then we have plus or minus. We can have an M sub L of plus 1 or minus 1. And so the funny thing about this is that you see this expression and it makes you want to throw up. And then you see the actual functions, and they're not too bad. Plus minus I. And then of course there's a Z. There's a Z component, which is okay. So with that, and of course there's I have you just Google these things, and that's your spherical harmonics. And then what you do is this whole thing is equal to some kind of quantum number, which is actually L times L plus 1. And then what you do is you solve this equal to L plus L plus 1, which again was done a long time ago by Bessel. It's impossibly similar to his 2D. This 3D version is almost impossibly similar to the 2D. So he solved that a long time ago. So I'll show you those solutions next time, because you got to go. And remember, you got other homework posted. And remember to download Mathematica. So homework 4 is advanced.